So in week 4 of Chemistry 30 Learning from Home, we're going to be looking at electrolytic cells and how we can calculate the mass of a metal that's actually been plated. But before we do that, let's just review quickly the differences between voltaic and electrolytic cells as long as the similarities. So we know that voltaic cells have a positive E cell. Electrolytic cells have a negative E cell. We know that voltaic cells are spontaneous. Electrolytic cells are non-spontaneous. We know that the energy changes are different as well. In voltaic cells, the energy change is chemical potential energy to electric potential energy, whereas in an electrolytic cell, it's opposite. We take electric energy in our power supply, and we'll use that to do some chemical change in our electrolytic cell. Things that are similar. Leora and Garoacat. Trying to remember what it means. Gain of electrons, reduction, that happens to the oxidizing agent, that happens at the cathode. Loss of electrons, oxidation, that happens to the reducing agent, that happens at the anode. So that's the same. Electron flow is still anode to cathode, so it will be always that direction. Anions move to the anode, cations move to the cathode. That is the same as well. But yeah, so most of the ideas are the same. The only difference is their E cells and the fact that voltaic cells are spontaneous, electrolytic cells non-spontaneous. I guess with voltaic cells, we have a porous barrier. And with electrolytic cells, we don't have one. So this week we're going to look at an application of electrolytic cells where we can actually plate a metal. Now, sometimes you'll notice in these cells we have the same reaction happening at the anode and the same reaction happening at the cathode. That's okay, because the whole point of an electrolytic cell is this, right? I want to take this fork, I guess, in this example, and I want to coat it in silver. Or maybe I have a bunch of, I don't know what these are, like tattoo tips or something, or a bunch of shiny things, and I want to plate them with chrome, or I want to plate them with some other metal because that metal has useful properties, but I don't want the whole thing to be made of that metal. That's kind of what this electrolytic setup allows us to do. Our anode is still the place where oxidation happens. So this electrode is our anode. We're losing electrons. Our cathode is still where reduction happens. When we are plating in electrolytic cells, that is happening at the cathode because that is where we're gaining electrons to form that metal. Setups. Okay, so here's a simple electroplating setup. What we're going to do is we are going to plate this coin, and we're going to plate it with copper. So because we want to plate it, that means that this is going to be our cathode. And at the cathode, we're going to take the copper ions, which are blue in solution, and we're going to add 2 electrons and cause it to become copper. Now, because this is a non-spontaneous reaction, I hook it up to the negative side of my power supply because I need to pump electrons onto this. They're not going to move that way spontaneously. I need to force those electrons onto that cathode. Now, because I'm losing copper in solution, so when I look at my anode, I'm going to replenish the copper ions in solution by using a copper electrode, and it's going to form copper 2+ as it loses electrons to the power supply. So there is my anode. Oops. I'll hook that up. Here's my cathode, and then I turn on my power supply, turn up the voltage, and I increase the current. And as this reaction happens, you'll see that this cathode is starting to form a layer of copper on it. At first it's kind of black, kind of like when we did that spontaneous reaction lab. But over time and as the reaction goes, it's going to look more like typical copper does as that layer gets thicker. Now, if we think about what's happening here, this cathode is going to increase in mass, and this anode is going to decrease in mass. If we look at these reactions, that amount that they increase and decrease should be the same because we're talking about the same amounts. Now, in order to find out the mass that's actually plated on here, we need to deal with things that we can measure. So this power supply, I'll just show you, it allows me to measure the current. So right now I have a current of 0.19 or 0.2 amps. So I can measure the current, and I can also measure the amount of time. So if I know the current and the amount of time, I can use some equations to calculate the moles of electrons that are actually involved in this electroplating setup. Once I know moles of electrons, well, now I'm dealing with amounts in chemistry that I can incorporate into my chemical equations. Now, in these electroplating calculations, there's two formulas. Well, basically one formula that we do need to know, and that's this one. So this is moles of electrons is equal to IT over F. So Ne is moles of electrons. I is current, and T is time. Now that's important because when we look at these electroplates, it allows me to find the moles of electrons. So current is something I can measure. That's in units of amps. Time I can measure. We need to calculate it in seconds, although sometimes it might be in hours, but we do need to convert it into seconds. And then F in this formula is the last thing. So F is Faraday's constant, which is 9.65 times 10 to the 4 coulombs per moles of electrons. And it's just the amount of charge for 1 mole of electrons. So all of these quantities allow us to find moles of electrons. Now, the reason why moles of electrons are useful, so if we look down here, in these half reactions that we have, so in the previous example, it was silver solid being formed, and this one it's copper, we have these electrons. Now, what this formula allows me to do is it allows me to take things like current, time, and Faraday's constant, convert it into moles of electrons, which I can then compare using these balanced chemical equations. So these moles of electrons are key between taking things that I can measure, like physics, kind of physics ideas like current, time, take these things that I can measure and convert it into a chemical kind of quantity, moles, that I can use to do comparisons in these chemical reactions. Everything else is still the same. If I want to find grams of copper, then I need the molar mass of it and things like that. If you are using unit analysis, there are some things you need to know. It's easier to not deal with amps in unit analysis. 1 amp is 1 coulomb per second, so that will help you with those units. Sometimes we need to convert between seconds and hours. Well, there's 3,600 seconds in 1 hour. And then this Faraday's constant. Now, this is in your data booklet. You don't need to memorize it. 9.65 times 10 to the 4 coulombs for 1 mole of electrons. Okay, so let's look at how we can, and this kind of gets back at what the unit of an amp is. It's 1 coulomb per second. So because amps is coulombs per second, use this in some examples. Maybe you want to pause it and try these questions on your own first, and then we'll do them together. So this first question is just a relatively straightforward calculation. So it delivers this many amps for 15 minutes, and we want to know the amount of electrons in moles. So our equation is moles of electrons, I don't know why I wrote that E down there, that negative down there, is equal to IT over F. So my current is 0.300 amps. Now time needs to be in seconds as well. So I know that 15 minutes, there's 60 seconds in 1 minute. So 50 minutes would be 900 seconds. So when I'm doing this calculation, so that's 0.3 amps times 900 seconds divided by Faraday's constant, which is 9.65 times 10 to the 4. Again, that's in our data booklet. So I can do that calculation, and I get 2.80 times 10 to the negative 3 moles of electrons. So that's kind of how we use that equation. Now, the big thing with this equation, which you'll see in the next couple examples, is it allows us to link these things and go back and forth. So this was kind of an introduction. This next one is more of a Stoich type question. So let's do this one together. I want to plate an antique teapot with 10 grams of silver. Now, just like other Stoich, when we do these questions, we need equations. So I want to plate it with silver, which means I want to form silver. So I want to take my silver ions and add electrons to them to get silver. The important thing that we get out of this is our mole ratio. For silver, it's 1:1, so that's relatively straightforward. For other examples, it's not, but it's still important to have that reduction reaction. So we want to find the length of time in minutes that's required. So we want to end with time, and we're starting with mass. So the first thing we have is grams of silver. Now, before I can get to time, if I have current, so I do have current, I have F, I need one other thing, so we need moles of electrons. So I need to first go from grams of silver to moles of silver. Then I can find moles of electrons, and then I can calculate the actual time. We are going to go up to this step, just using unit analysis like we have, and then use the formula to find time at the end. So I have 10 grams of silver. My first step is to convert between grams of silver and moles of silver. So I need the molar mass of silver, which is 107.87 grams for 1 mole. So I've done that first step. I can look at the units, grams. I have moles of silver. Then I use my equation. So don't forget this step. I know in our titration stuff, sometimes we forgot about this mole to mole step. So I want to change the chemical. I want to get rid of silver and find how many moles of electrons that is. In this one, it's not going to cost us because it's 1/1. But sometimes there will be like a 1/2 or a 2/1. Okay, so now we have moles of electrons. So we've gotten to this step. I'm going to put this in my calculator as it is. So 10 divided by 107.87. So I know that this is 0.0927 moles of electrons. I don't know why I put this under moles of electrons. Our next step then is to find time. So we have this equation, moles of electrons is equal to IT over F. I want to find time. So I'm going to rearrange this equation. I'm going to multiply by F, so moles of electrons times F. I'm going to divide by I, and that will give me my time. So I have moles of electrons here. I'm going to keep that in my calculator. F is Faraday's constant. That's 9.65 times 10 to the 4. And I divide by I, my 1.80 amps, and I will get the time. So I do that calculation, and I get 4,970 seconds. It does ask for minutes, so I'll divide that by 60, and I get 83 minutes. So this was an example where we had to do this calculation. Moles of electrons is IT over F at the end. Sometimes we'll do it at the start. But the link there, so the reason why we use that calculation is it allows us to go from moles of electrons to time. So sometimes this step might be at the start, sometimes it might be at the end. That's where this equation's in time. So one more here. We have a chloroalkali cell. We want to find the mass of chlorine that's formed. Now this one's a little bit different because we have two gases being formed here in this electrolytic cell. And we want to know what mass of chlorine is formed. To form chlorine now, this is going to happen at the anode, right? I'm going to have two chloride ions, and they are going to lose 2 electrons and form Cl2. So this is the equation that we need. We know we have 55 kiloamps. That's going to be 55,000 amps. And it happens in 8 hours. So 8 hours, there's 3,600 seconds in 1 hour, is 28,800 seconds. Now in this step, so we have enough information first where we want to find moles of electrons. Once we have moles of electrons, then we can find our moles of Cl2, and then we can find our mass of Cl2 at the end. So in this question, our first step is to find the moles of electrons, which is IT over F. So I, which is 55,000, times T, which is 28,800, divided by 9.65 times 10 to the 4. And I get moles of electrons, 16,415. I rounded that last digit, moles of electrons. So I'm just keeping that in my calculator. We got here. Now we can kind of set up our unit analysis and do Stoich. My first step, again, is to change what chemical I have. So I want to get rid of moles of electrons, and I want to find moles of Cl2. That comes from my balanced equation. And this is why it's important to have it, because I have 2 moles of electrons for 1 mole of Cl2. So I do need to divide that number by 2. And then my last step is to find grams of Cl2. So now I need the molar mass of Cl2. Remember, it's Cl2, so that's important. So it's 35.45 times 2. That's 70.9 grams is the molar mass. So I have my moles of electrons divided by 2 times my molar mass is a really large number, which should make sense because it's a long time, a lot of current. Like, this is an industrial process. So I do that calculation, I get 581,894. Probably makes sense to write it in kilograms, so that would be 582 kilograms of chlorine that would be produced. So now we use moles of electrons as IT over F at the start to find our moles of electrons. Once we have that, now we are converting the units. So I use my balanced equation to find how many moles of chlorine that is, and then use my molar mass to find how many grams of chlorine that is.